Hello and welcome to this lesson on some of the common number sets that we find in math. We'll be looking at 8 sets of numbers in particular. The first set of numbers are the natural numbers. Now the definition that I am used to is that the number 1 is a natural number. If x is a natural number, then x plus 1 is also a natural number. And that this is the smallest set that meets these criteria, for as well as we could define the term smallest. Note that this is the Western convention. In the Eastern convention, the natural numbers start with 0, and we do not use the set of whole numbers. This convention actually makes a little more sense when it comes to building numbers with set theory and doing it rigorously and formally. But I was raised with the convention that we start at 1. So the natural numbers are 1, 2, 3, 4, etc. So that is the convention I will use. The whole numbers are the next largest set. Every natural number is also a whole number, and the whole numbers also include 0. That's the complete definition. So the whole numbers are 0, 1, 2, 3, and so forth. Now, the integers are our next set. Every whole number is an integer. The negatives of the natural numbers are also integers. So in addition to 1, 2, 3, we have -1, -2, -3. And note that in some high schools, particularly those in North America, the letter I is used for integers instead of the letter Z. This is a side effect of old wartime politics that will not continue at the post-secondary level. At least that's what I've heard about the origin. The formal mathematical community uses Z because these were first developed by German mathematicians, and the term for numbers in German is Zahlen. Now the rational numbers have the symbol Q. Think of Q to stand for quotient, since they are fractions. In fact, that is the definition. You can write it as the ratio of two numbers, and these are numbers in sets we have already defined. So fully simplified, so when you've reduced your fraction, it can be written as an integer divided by a natural number. And the decimal representations are either terminating or repeating. Note that saying we're dividing by a natural number excludes division by zeros. All integers are also rational numbers with a denominator of 1. Now the next set of numbers are the real numbers. Every rational number is also real. All numbers which could fit on the number line are real numbers. In a way, that is the way we define it. The real numbers will also satisfy 13 axioms. Now, an axiom is something that doesn't need to be true, but mathematicians have chosen to treat it as true, at least for the current context. There are 11 axioms that describe an algebraic field, and we add 2 more to uniquely define the real numbers as opposed to using the rationals or other sets we'll deal with. The first axiom is that the sum of 2 real numbers is a real number. Axiom 2 says the product of real numbers is a real number. Axiom 3 is what's known as the commutative property for addition. If a and b are real numbers, then the order doesn't matter when you're adding them. 1 plus 2 equals 2 plus 1. The same is true for multiplication. That's our axiom 4. A times b equals b times a. We're going to notice a pattern here. For the first 10 rules, we'll have a rule for addition and then the matching rule for multiplication. Here we have the associative properties. If we have 3 real numbers, and we're adding all 3 of them, we can start by adding the first 2 or the second 2 will have the same result. So if you're adding 1, 2, and 3, add the second 2 first, you get 1 plus 5, which is 6. If you add the first 2 first, you get 3 plus 3, still 6. Similarly, when you multiply 3 numbers, if you multiply 2, 3, and 5, well, you can have 2 times 15 or 6 times 5. Either way, the result is 30. Now, if a is a real number, then a plus 0 is a. So adding 0 does not change the identity of that element, as they call it, in the set. The matching multiplication rule says that multiplying by 1 does not change the identity of the number. Now, if every number a has an additive inverse, such that a plus negative a equals 0, this is axiom 9. And we will use a minus b as shorthand for a plus a negative b. So the operation of subtraction is not often formally discussed because it's really just adding the negative. Now the magic rule for division is how we could start to tell the operations apart. If you didn't already know what the symbols for addition, multiplication, 0, and 1 meant, you would not be able to distinguish addition and multiplication to this point. This is how we tell them apart. When we're adding, every number has a negative. But when we're dividing or multiplying, not every number has an inverse or a reciprocal. 0 has no reciprocal. You cannot divide by 0. But a to the negative 1 or 1 over a are inverses. So you could take a times 1 over a and get 1. And a divided by b is a shorthand for a times the inverse of b. Now for these first 10 rules, we had either addition or multiplication, not both. For rule number 11, we have both. This is called the distributive property, and it's how addition and multiplication mix. So if you have a number outside the brackets, multiplying the sum of numbers inside the brackets, that number on the outside has to multiply both numbers on the inside. You can actually combine this with the anything plus 0 is the same thing rule to prove that anything times 0 is 0. In this case, if you take that a times b plus c, where c is 0, you can do the b plus 0 part first, and then just have a times b, or you can do the distributive property first and have a times b plus a times 0. And they have to be equal to each other, so if ab equals ab plus 0a, then 0a has to be 0. It did not change the identity of ab. Now these last two axioms are the ones that extend the axioms of the algebraic field to uniquely describe the real numbers. So one of them is that all real numbers can be written on the number line. This is properly known as the well-ordering principle, and it's formally phrased as, if a is less than b and b is less than c, then a is also less than c. So they stay in order. You don't have a rock, paper, scissors situation. And then the final of the 13 axioms that define the real numbers is that the number line has no gaps. Every spot on the number line is home to a real number. That's not true for the rationals. Pi and the square root of 2 are not rational numbers, and yet they're on the number line. So the real numbers include pi and the square root of 2 and other irrational numbers just to fill in the gaps. Now the irrational numbers themselves are all real numbers which are not rational numbers. Notice that the symbol is that quotient q, but with a line above it. So the irrational numbers include the square root of 2, the cube root of 28, and any other imperfect roots. Square root of 4 is a perfect root, so that one's rational. And in mathematical logic, a line above a symbol means not. So an x with a line above it means it's not x. That's the origin of this q with a line symbol for the irrationals. If you write the decimal representations, those decimals will neither terminate nor repeat. And the imaginary numbers are the ones that properly have that symbol I, not the integers. So the square roots of negative numbers are the imaginary numbers. So they're expressed as multiples of I, where I is the square root of negative 1. So the square root of negative 4 is 2i. So really, they're just like any other numbers, but if you take the square root of a positive, you get that radical. Take the square root of a negative, you just add an I to the answer for the positive number. They form their own number line, but you can't make a complete algebra out of them because 0 and 1 are not imaginary numbers. You can use them in algebra, but they have to be part of a larger set of numbers. The idea that you can have the square roots of negatives was so hard to accept initially that they decided to name them almost by accident. It was mathematicians mocking each other. You can work with those imaginary numbers if you want to, but I work with the real numbers, that kind of thing. So that's why imaginary and real got named first, and why real got the R before rationals did, although for a time there was a lowercase r for rational and a capital R for real, or vice versa. So these may not be intuitive, but they are valid and they occur in nature. When I was doing research in physics, I measured them in the lab. They are as real as any other number. Now the complex numbers with the symbol C are the sum of real and imaginary numbers. So A plus BI. So A and B are both real, but that BI combination makes it imaginary. And they adhere to 12 of the 13 axioms that define real numbers. They do not all fit on a number line, but they can be plotted in the Cartesian plane. But if you use the real and imaginary parts, you use them as typically real on the x-axis and the imaginary numbers on the y. And that would allow you to put the complex numbers in the plane with the coordinates, and then you can make a consistent algebra. You just have to remove axiom 12 from the real numbers. That is the way most advanced algebras actually work. If you want an algebra more complicated than the one we had with these 13 rules, you usually make it by taking rules away. It's extremely difficult to add rules to that set without breaking everything. But these are the 8 most common sets of numbers that get used day to day and their definitions.